Okay, welcome to the second week of the course on curves and surfaces. So, this will start with surfaces. And as we have said in the beginning, we will be dealing with the surfaces in R3 only. So, before giving a formal definition of a surface, let us try to see what we understand by, in general, what is our notion of a surface. Well, we first of all, we all live in this world and we know this world is kind of a sphere or ellipsoid. And we are kind of here. And we walk, we stay, we move around. On such a, in general we call it surface. Also we know our world is 3 dimensional, and if I take a plane, our intuitive notion will say that such a thing is a surface. But also, perhaps you are climbing in a mountain, then you will encounter a surface like this. So, to come up with a definition, what we do, as we did for the curves, that we actually talk of so called parametric surfaces. What does it mean by that? That we define our surface. For instance, you will see, I will do examples today, 3 examples to tell you that we need to define a surface locally, in the sense that, okay, so surface in general will be a subset of R3. So, I will call it S is a surface if for every point P in S there exists open set U in R2 and open set W in R3, P belonging to W, such that there is a homeomorphism sigma from U to S intersection W. So, what does it mean? That okay, I may have a surface, very rough surface like that, in general terms, but I am viewing surface from my, I am standing in a plane visually R2 and I am viewing it from the plane. So, any point here P well, this W may go out and I will have a U on the plane, not on the real line, okay, on the plane, such that I have a map sigma which maps U to W intersection S, that is precisely this portion homeomorphically. And what is an homeomorphism? I hope you all of you knew what is a homeomorphism. Homeomorphism between two open sets means sigma is 1 1 onto continuous with a continuous inverse. Such a thing we will be calling a surface. It defies our notion little bit in the sense that, okay, if I am in a plane or on a sphere, why you have to define it locally? I mean, what is the reason for that? You will soon see. Let us start with some example. Let us take the simple example plane. You will see that for the plane I do not need to define it locally, but when I move to sphere, there will be actually problem to, I mean, you can intuitively understand that you cannot put the sphere, you cannot flatten the sphere on the plane. So, okay, let us talk about some examples. Plane. What about a plane? So, let us take a plane P. So, I draw the coordinate axis. And I have a plane here. For reasons, I just take it most simplest one, and I take a vector here. Let us say A in the plane P. So, this is my plane P. Now, how do I describe this plane P mathematically? Okay, I take a vector A here in the plane P and I take two parallel vector along the axis P and Q. So, and I take unit vector P, Q, unit vectors perpendicular to each other and both parallel to the vector A I have taken in the plane P. So, in this simplest example I have taken jet plane and A is a vector, unit vector around z or any vector around the z axis, and P and Q you can take unit vector around x axis and y axis. Now, you observe any vector parallel to P is, what will happen to that? Okay, P and Q are parallel vector. I have already taken a plane and A is the vector on the plane. So, it will be of the form some u p scalar u plus v q u and v belonging to R. So, if R is any unit vector or any positive vector, R is in P, then R minus A is also in the, so here is R. R is another vector here. So, R minus A, so this will be parallel if I draw it very clearly here, it will look like I have taken this vector to be A, this is my P, this is my Q, and I take any vector R on the plane P, then R minus A, which is, this is R, so this is R minus A, this is parallel to P, correct. So, R minus A will be of the form u from the above observation v plus q, which implies R will be A plus u p plus v q. So, R is a general vector in the plane I have described as R equal to A plus u p plus v q. So, fixing any p and q, I can describe my sigma now, sigma u v is equal to A plus u p plus v q. So, this will describe my plane completely. And my u is, what is u here? U is R cross R, which is an open set in R2. Okay. So, every point I can describe by one particular u, one open set does. But let us move to the example of a sphere, and it is better explained on the board. So, next example is sphere. Let us take unit sphere, which we will be denoting by S2, which is all points x, y, z in R3 such that x square plus y square plus z square equal to 1. So, if I draw it, it will be like this part is not visible if when we see it as a globe. So, this is the sphere. Okay. So, now you need see any point here on the sphere x, y, z. If I look at this part, whatever doing this part, that is I draw this colored line. This part we called upper hemisphere and this part we called lower hemisphere. Just think of our world, I mean our globe. Any point here z, x, y, z, is related by the notion, is related by the relation correct, because x square plus y square plus z square equal to 1, whereas if I extend it and any point here z is minus so what is happening here? According to our definition, if I take sigma from u, where my u is 0 1 cross 0 1 to R3 sigma xy equal to x y 1 minus x square minus y square, then this will cover the upper hemisphere of the sphere. And similarly, I take sigma tilde from same u to R3 this will cover the, so this will cover upper hemisphere, this will cover lower hemisphere, but the points on this great circle, that is the equator, that will be covered by both, and we should keep it in mind that these are covered by both. But if you can see that these both of them are homeomorphism restricted to, so if I take an open set which is restricted to upper hemisphere only, sigma is homeomorphism, on the lower hemisphere sigma tilde is homeomorphism, but this homeomorphism has intersections, sigma and sigma tilde are not disjoint. This will prove to be a very crucial point in our discussion ahead, that I covered this H2 by two homeomorphism, sigma and sigma tilde, and they have intersections. Actually, you learn in school that you do not do this thing, you do not describe the globe this way. There is another way to describe the globe, that is by longitude and latitude, which is called cartographic description. That I mean, suppose we are in a particular place in the world, we say okay, it is 72.21 degree north and say 58.32 east. So that is the way we describe places in the world, and that uniquely describes that. Let me give that cartographic descriptions of sphere. The reason I am doing it, that you will see that first of all we cannot cover sphere by one single homeomorphism, and secondly when we cover by different homeomorphisms will have intersections. So, here is the sphere again. And I have a place somewhere here. What is the latitude? Latitude is described by this angle theta, right? Z and y, this, no, not really. This is theta, sorry, this is the place, and then I project it on the xy plane. I join this. So, theta is this angle, this is theta, and longitude is the angle between x and z axis, that is this angle phi. And we have a Mediterranean line, the great circle passing through like this, and according to we move east or west, we call it the longitude east, this way longitude phi east, phi degree east, and if you are on the upper hemisphere, we call latitude theta degree north. And how do you cover it? What is the range of theta? So, to cover S2, the sphere, you take theta okay, sorry, I should make it open. And phi between 0 to 2 pi. So, u is theta phi as above. But then you see there is a problem that I am not covering the entire sphere, because my definition of surface is that I should make it sigma from u to S2 intersection w. I choose my w, and u should be open set. But make it open, I am missing out certain points in the sphere. What point I am missing out? So, what are points we are missing out? You decide it. I will give you the answer in the next lecture or next to next lecture, but for the time being you just think about yourself what are the points you are missing out, and what is my sigma theta phi, that you can usually see. This will be cos theta cos phi cos theta sin phi sin theta. I think you have learned it in your class 2 courses that this is the usual parametrization of the sphere. But as we are missing out certain points, actually I need another sigma to cover the entire sphere, which is minus cos theta cos phi minus sin theta and minus cos theta sin phi. Sigma and sigma tilde together covers S2, and there will be many points in the intersection. So, what are the points in the intersection? So, this is my second example, and next I want to end this lecture with another example with a surface. I do not know if it is a surface or not. So, this is called a double cone. This looks like well, how it will look like. If I draw like this, then this will be I draw better on the board. Well, let me draw it on the board. So, decide if S is a surface according to our definition. So, this lecture was the introduction to very basic examples of surfaces, plane and sphere, and double cone. I do not know it is a surface or not. Next time onwards we will try to make it more formal. Okay, that is it.